Okay, so I'm gonna go over 4.1 and 4.1 vector space. Is it vector space? And subspace. Okay. Vector space is definitions. Definitions, vector space. A vector space is a non-empty set. V. Okay, V. We just say V. Okay. Together with two binary operations. Additions and scalar multiplications. Okay. And scalar. And such that there are 10 statements satisfied, must be satisfied. So first one, vector u plus v. Let me use a v. This is v. Okay, this is v. Is in vector space. So for the for given vector u and v in vector set v, the u plus v is in that set. Okay, that's the meaning of that. The second one, and the u plus vector u is equal to u plus v is equal to v plus vector u. Okay. And once it means that the vector space satisfies commutative property. The second next one, u plus vector v plus w is equal to u plus v plus vector w. So it means that the vector space satisfies associative property. And then next one is there exists zero vector. There exists, that means there exists zero vector such that u plus zero vector is equal to vector u. This vector u is identity, okay, identity in addition operator. This is called the identity in addition operator. Okay. The 5 for each vector u in vector space V, there is what? Minus u, okay, in vector V, such that u plus minus vector u is zero vector. Okay. And then 6. So 1 through 5 is the statement for addition operations. Okay. The 6th one is scalar multiplication. C times u is in vector v. It means that if vector u is in vector space V, then scalar multiplication is also in vector space V. And 7, C times vector u plus vector V is in CU and then plus CV. Yeah, that means this is a scalar associative property of scalar multiplication. And then C plus D, the vector u is equal to CU plus DU. This is discrete property of the scalar multiplication. 9, C times DU is equal to CD times vector u. Okay, that's an associative property of scalar multiplication. This is associative, distributive, and then that's just distributive, okay? And that's the commutative, associative, okay? So then the last one, 10. 1 times vector u is equal to vector u. So here 1 is 1. This is identity. In scalar multiplication. Okay. So these are related to scalar multiplication. Okay. Okay, so now definitions. Next one is the subspace. Okay, subspace. Okay, subspace vector of a vector space V is a subset H of vector V. Okay. So subspace is a subset. First one, sub should be a subset of vector space V and satisfy these property. There's 3 property. First one, 0 vector must be in the set H. I'm talking about the conditions that the subs in order to be the subspace. Okay. So first one, let's say H is a subspace of vector V. V is a vector space, okay? Then first H must be subset. Second one, the 0 vector must belong to that subset H. Okay. Or the 0 vector is in vector V. The second condition is the U plus V is in H, or any vector U and V is in vector V. So H. So when you pick the 2 vector in H, then sum of that vector must belong to H. Okay, for any given 2 vectors. The third one, C times U is in H. So for all vector U is in H. So in the C, definitely C is in C must be real number. Okay. So basically, in order to be the subset of vector space is vector subset H in vector space V, the subspace, then 0 vector must be in that subset H, then the addition and then scalar multiplication must be satisfied. This is addition, right? This is a scalar multiplication, right? Then that subset H must be subspace. Okay, so easy example. So first one, the vector space. Give me a second. 1, 2, and 3. 1. The vector space R2. R2 is vector space? Yes. Well, you got it. R2 is vector space. So you know, if you are wonder the vector space R2 is a vector space, please check this condition statement 1 through 10. Okay. So R2 is a vector space, but that is not a subspace of R3. This is not a subspace of R3. Okay. How come? Because anyone can tell that why vector space R2 is not a subspace R3? Why? R2 is not a subspace R3 because R2 is not a what? Subset of R3. A subset. So if you when you want to figure out whether or not the given vector space is a subspace of R3, you should check that vector space is a subspace of the other space. Okay, that's the very first thing you have to do. It's not a subset of R3. Okay. So R2 is what? R2 is going to be the set of all x1, x2, just 2 by 1 column vectors, such that x1 is R, I mean x1 and x2 is in R. But R3, what is that? This is a set of what? X1, x2, and x3. Just column vector whose who has 3 entry, right? 3 by 1. Such that x1, x2, and x3 is in R. Is it? Okay. The second one then, what about this? Let H be the set of all x, y, 0, the set of all these that column vectors. Okay, x and y is in R. Okay. Then show that this is then that's going to be a subspace of R3. So here's a question: show that H is a subspace of R3. Okay. All right. Here's a solution. I mean, proof. First of all, we have to show that what H is a subset. Okay. H. What? Question: is H a subset of R3? Do you think that? Yes. Right. Right. H is in what? R3, isn't it? Not equal, but R3. The second one, question, what? Zero vector is in H. Let me prove it. Zero vector is what? First one, zero vector means that what? 0, 0, 0. Because we have to take the zero vector from the vector space R3. So it should have 3 entries. Like this is in R3. And what? Zero vector is in H when x and y is equal to 0, right? This is a real number. So when x and y is 0, then x, y, 0 is going to be zero vector, and the zero vector must be in H. Okay, third one. Question. What u vector u plus vector v is in H, or well, u and vector v is in H. Right? So I mean that's yeah, this kind of previous, right? I mean obvious. I mean this is proof. Okay, so let's say vector u is equal to u1, u2, 0, right? Okay, and vector v is equal to v1, v2, 0. Okay. And then u plus vector v is equal to u1 plus v1, okay, u2 plus v2, and then here's 0. 0 plus 0 is 0, right? And this is equal to this belong to H because what? Because u1 plus v1 is in R, and u2 plus v2 is in R. Okay. The last one, we have shown that I mean, so we say that, oh, by the way, I forgot to mention this. We say that this subset is closed under the addition. Okay, that statement is we say that the subset H, or we can say subspace H. I think subspace H is closed under the addition operator. Okay. Similarly, well, third statement, we say that the subspace H is closed under the scalar multiplication. Okay, that's what we call. So now that subspace H is close to addition operation. And then we have to show that, well, that subspace H is closed under the scalar multiplication, right? C times the U is in H, or vector U is in H, right? And C is in real number. Okay. That's also, yeah, this trivial, because C times vector U is equal to what? C times U1, C times U2, and the 0. This is in H, because, well, C times U1 and C times U2 is what? Is in real number, the set of real number. Okay. So there is a lot of examples in textbook. So this is a really simple one. So please take a look at every single examples in the textbook, okay, to fully understand the subspace. And there are a lot of useful and then impressive examples in textbooks, okay? And then theorems 4.1, and then give you the connection between the span and subspace, okay? So that's the definition of subspace.